We know that transfer path analysis, a lot of the questions are complicated, so we do ask, there is a Q&A section that you guys can see. We do ask that you guys do please put questions in, and we will be getting back to you promptly, either with a direct phone call, if you like, or in an email. So yes, please do send in the questions. I'll turn it over to Adam Garza. By the way, my name is Eric Petersen, and I am sales manager here for our NVH sensors out of North America, Novi, Michigan.
Okay, thank you, Eric, for that quick introduction. And again, thank you everyone for joining today for this webinar. Today we're going to be discussing transfer path analysis within the automotive field. So within automotive, transfer path analysis is being used more and more to address several NVH aspects from troubleshooting to development through prototyping and predictive analysis. In general, TPA requires measurement tools. Their choice and accuracy is key for accurate and successful TPA. And Kistler offers several sensors which are and can be used for TPA in automotive. And the goal of this webinar is to provide an overview together with a review of the strengths of our sensors to support the best TPA measurements. We have an agenda list here on this slide, just to give you an idea of what we're going to go through. So we're going to start with a brief introduction to TPA, and then we'll go into acceleration measurement, force measurement, wheel force measurement, and then we'll have a quick wrap up at the end. So that being said, I would like to introduce our presenter for the day. Dr. Roberto D'Amico is the business driver for NVH in the vehicle testing business unit at Kistler. Roberto holds a PhD degree in noise and vibration from KU Leuven in Belgium, and he has about 15 years of experience in NVH with a focus on automotive. So with all that said, I'd like to hand it over to Roberto to begin his presentation.
Thanks a lot, Adam. Thanks a lot, Eric. Hello, everybody. I wish you good day or good afternoon, depending on where you're sitting today. And let's jump into the first section of this webinar, which is about, it's an introduction, a very short introduction to transfer path analysis, just to set the scene and to talk later about the measurement. So talk about the sensors. And for those of you who are experienced, very experienced in transfer path analysis, you might want to excuse me, because I will just do a crash course in transfer path analysis and try and really to pick up the key elements for me to really set the scene, as I just said. To do that, I have to start from a basic concept, which is mostly known in the NVH area. So the relationship between the link that exists between the source, the transfer, and the receiver. So whenever you are measuring something at the receiver point, you are actually getting a contribution from sources, which in automotive, they are quite common and always the same, like an engine or a motor or wheels, gearboxes, and so on. And this information, this excitation gets transferred to the receiver through transfer functions. So to basically what we call usually FRFs, let's say. And now it is important to have a look at this concept, because this is just the underpinning concept for transfer path analysis. And why is it important? It is important because in automotive, it can answer many questions. Like, for example, if you have a resonance on your system which get excited by the source, you might end up in a situation where the receiver shows a very high amplitude of vibration, or maybe very high sound pressure levels. Therefore, you might want to have a look at that. You might want to understand how to reduce these overall amplitude of vibration, or SPL. On the other side, maybe you have a situation where you might have a resonance, but you're not exciting it. Therefore, the measured vibration is not really giving you a problem. So it's not jeopardizing your targets or something like that. And therefore, it is important for you as automotive engineers to understand very well what is the relationship between sources and how they get transferred to the receiver. And this is the reason why transfer path analysis is gaining more and more importance in the automotive field. Actually, the type of challenges that are present in automotive NVH, to which transfer path analysis can give an answer, are some of the following. So, for example, what source is contributing most to the receiver? So, what is it contributing most to the wheel? Is it contributing most to the engine? And for example, which are the main transmission paths that bring the vibration from the engine mounting to the driver, for example, and how sources and paths interact with each other. Another very important question in automotive is it a structure-borne or is it an airborne issue? And it is important to differentiate between these, because then there will be different type of measures that need to be taken. Therefore, it is important to understand the contribution that is coming from a source and how it is traveling till the receiver. And of course, typical applications of transfer path analysis involve vehicle development, troubleshooting, prototyping, validation, target setting, and even nowadays more and more predictive analysis, where we're actually trying to understand how different type of sources or how different types of receivers, of body whites, for example, would respond when combined together, and sometimes even not even physically combining them together to measure them, so measuring them separately. And to all these points, transfer path analysis provides an answer. And because all these points are very important, you can easily understand why transfer path analysis is becoming more and more important in the NVH field, in the NVH automotive field. Now, let's start diving a little bit deeper, and let's start really setting the scene here. When you talk about transfer path analysis, there are three key elements we need to consider. So let's have a look at this schematic representation of a vehicle with a source here, which could be the engine, which is running, and then a receiver. So the source, we would call it active source. In TPA, we assume that this source is actually vibrating. There is often also the assumption that is made that this source, what is generating the vibration of this source, might not even be known, but we are not really interested in that. Like take, for example, an engine vibrating, so an engine that is running, vibrating engine that is running. You assume that what is happening in the combustion chamber is not of primary interest for you. Of course, at Kistler, we do know that you can measure the combustion pressure. We do have a huge product line for pressure measurement, but we assume that the vibration that is originating from the engine is transmitted through a receiver via an interface point. So the interface really creates the connection for the vibration transmission through the source and the receiver. And the receiver is just a passive element. So the receiver is not exciting back actively the source. So it's just an element through which then vibration are flowing, basically. Now, having said that, having described these, we can use a little bit more mathematical formulation to, again, allow me to explain a very basic concept. And I promise in this presentation, you're not going to see too many equations. I'm not going to have the time to go through that. But it is important to underline that whenever you have a response, U, for example, at a certain point, this is in general given by the contribution of the sources, which are transmitted by the admittances. In this case, the admittances are related to the receiver plus the source together. So it's considered the system as a whole. And this is a concept that should be familiar to most of you. The fact that basically the sources are traveling through transfer functions till they hit a receiver. And this is also what the concept that I presented at the very beginning of this section. And now, when we look at TPA, generally TPA requires measurement, of course, and analysis. And at the measurement level, we always have operational measurements where we need that the source is actually running, so that the engine in this case is running, and FRF measurements where actually the system is at steady, so it's in a steady condition. Then we have an analysis phase where we bring this information together to analyze and understand better loads and the sources, the paths, or maybe even make predictions of the performance of the overall system, probably with even multiple components, different components mounted on top. And over the decades, engineers and researchers have developed a wide variety of TPA approaches. And I find that they are nicely classified in the paper that I reported at the bottom of the slide, and which I follow, and have basically differentiation in classic TPA, component-based TPA, and transmissibility-based TPA. So these three groups of TPA cover the variety of different TPA methods. And now the goal is that we go through each of these very quickly, just to see what is the role of measurement techniques in each of these, and to see what are the different differentiating factors. Let's start with classical TPA. In classical TPA, as I said, you have a testing phase and an analysis phase. During the testing phase, you're going to have operational measurements and FRF measurements. During the operational measurements, what you want to do is that your source, you're going to take your source. So in this case, it's your engine, and this is actually running. So you want to have it running. And what you want to measure is the interface forces exchanged by the source and the receiver. So at the end of the day, you want to make sure that you get this information out of the test. And this is done with a variety of methods, for example, with direct force measurements, or maybe with mounting, with mount stiffness method or matrix inverse methods. All of these require different types of measurements and putting data in different ways together. But what you want to get at the end of the day is the interface force. And this interface force is always dependent on the source and on the receiver. So there is this strict dependency, which is very important to understand classical TPA. From a measurement perspective, what you're going to use mainly for this type of assessment is accelerometers, of course, and force sensors. So the most used tools are these two, actually, to measure the interface forces. Then we move to FRF measurement. And usually here, I guess most of you are familiar with this type of measurements. We are taking just the receiver and measuring the FRF from the interface to the receiver in this case. And for this, you would need, of course, accelerometers or even microphones. Sometimes force sensors, it's a little bit more rare. And then you have tools to excite the structure, like impact hammer, shakers, for example, with impedance heads and acoustic sources. Then we move to the analysis phase, and here is where we bring all together. So to predict the behavior of the car with the engine at point U3, we are bringing together the information we just measured. So we will bring together the FRFs, so the admittances, and the interface forces we measured on the receiver earlier on in the operational measurement. Now, this is interesting because it tells us more about the sources, and it tells us more about how these sources are contributing to the receiver. But of course, if we want to change the engine and maybe check another engine, how would impact the performance at the receiver, we are not able to do that because classical TPA mainly allow us to do this analysis on a certain couple of source and receiver. And this is why researchers and engineers have been working to formulate TPA in a way that you can actually measure the source independently from the receiver. So in component-based TPA, what you do is something which goes in the same direction in terms of process breakdown. So we have test again, and then we have operational measurement and FRF measurement. During the operational measurement, what you want to measure is the force, interface force of the source, which is invariant to the receiver. And to do that, you actually can use different techniques. So for example, you can use the blocked force measurement, and this at the moment is on the hype. There are many instances in which you want to measure the block force. And this basically consists into attaching the source, vibrating source, to a very rigid block. Of course, in reality, an infinitely rigid block does not exist, but this is a block as rigid as you can actually design theoretically. And there you're going to measure an interface force, which is not related necessarily to the final receiver. An alternative method is the in situ method, where you're trying to decorrelate the force you're measuring from the from the fact that here you would have a rigid block. So you can even have a receiver, and you're still getting an information which is invariant from the receiver itself. So very powerful approach. and nowadays is becoming more and more important. I again suggest you to have a look at the reference at the bottom of the slide to understand a little bit more about these methodologies. Sometimes there is also a free velocity approach that is used, but this is very seldom the case. The nice thing in this operational measurement is actually the fact that we should not necessarily relate the source to a certain receiver. So we are measuring it separately from the receiver that we're going to have at the end of the process. And to do that, we're going to need, of course, accelerometers and force sensors from a measurement perspective. Then we have, again, FRF measurement. And here, depending on the formulation of TPA you're going to use, you might have a source attached to the receiver while you're doing that. But as we will see in a second, there is also a way to decouple them. And the tools you're going to need from a measurement perspective are still the same as I mentioned before. So accelerometers, microphones, and of course, tools to excite the structure like shakers, hammers, acoustic sources, and so on. Once we have these two information, so the forces and the transfer functions, we are going to put everything together to predict the response of the whole system. And here, actually, you can, of course, combine the admittances of the two systems and the forces that you calculated during the operational phase. Or alternatively, by manipulating the equations, you can actually get to a standpoint where the source and the receiver, the information related to the source and the receiver are separated. And this opens up extremely interesting possibilities even in the way OEMs, so car manufacturers, are interacting with the suppliers. Because of course, if you are able to measure a source separately from the receiver, then it means that suppliers, for example, can provide certain information to OEM without necessarily the OEM having to test the whole system. So you see that the reason why the component-based TPA is nowadays the most used TPA approach is clearly because it offers some practical advantages. And you're going to have information regarding the loads and information regarding the paths about your system. So you have basically everything you might want to have from this type of analysis. We have a third class of TPAs, which I refer to them as transmissibility-based TPA. Here we have operational TPA, but there are also other types of TPAs like OPACs that has also been developed. Here, basically, what the purpose is to economize on the test setup and on the testing time, because as you have seen in the previous two classes of methodologies, you have to actually set up multiple tests to perform a TPA. And in this case, what we are going to do is to place accelerometers, for example, or sensors in the neighborhood of the interface point and at the receiver. And we're going to run multiple rounds of excitations so that we can actually enrich the statistics of the data gathered by the sensors and get an understanding of the transmission between these points that are measured close to the interface and the receiver. Therefore, at the end of the day, after we have performed an operational path analysis, we would have saved a lot of time, but on the other side, we would only have information related to the paths, not to the loads or not to the interface loads, for example. To do that, you can use, from a measurement perspective, accelerometers, force sensors, of course, and OTPA is interesting because it easily allows to combine also other types of sensors, like, of course, microphones, but also strain gauges to enrich even more the data set. Now that we got this far, that I gave you this really crash course in TPA, I want to try to summarize a little bit and make some considerations here. So let's have a look at the table at the bottom of the slide. Here we've got the three classes. So we have classical TPA, which requires operational measurements and that should provide the interface forces on the source plus the receiver. You need to perform FRF measurements on the receiver, and what you can get is load identification and contribution paths. It is a very simple approach, but it is only related to a specific receiver and source couple. So you cannot test additional sources, for example. To do that, to overcome this limitation and to actually generalize and try to make your source independent on the receiver, you can use component-based TPA. There, of course, you have operational measurements where the interface force is invariant of the point which is attached to. We have in the FRF measurements, the measurements that can also be carried out theoretically on R and S separately. And then we have a wealth of possibility on the analysis side, because you cannot only do load identification and contribution paths, you can also do performance prediction. Because of course the source is independent on the receiver, then it means that you can either apply multiple sources to your receiver or get information about, in fact, multiple sources and maybe model the transfer as you wish. We have a third methodology group, which is transmissibility based, which tries to economize on the testing effort, I would say. You don't run FRF measurements, you just measure the transmission between a certain group of sensors in the neighborhood of the interface usually and the receivers. And there, of course, you at the expenses of a shorter and more efficient testing, you will sacrifice the information about the loads and possibility to performance prediction. So your information are mainly limited to the contribution paths. And now, having said that, I mean, these type of methodologies are widely applicable to automotive NVH. Here in the picture, I just report a few which are very common. I mean, even if you search in the literature, I'm pretty sure you're going to find applications that are related to engines, motors, auxiliary drives as well, steering columns, and more tires and suspensions. So these are very common because, of course, when it comes to automotive, these are the main sources of noise, and you want to characterize, model, and engineer how these sources contribute to the overall performance of the vehicle. And when it comes then to the measurement technology, the typical measurements, of course, are acceleration. Forces and moments are very important. These are exchanged, especially at the interfaces, and you might want to characterize them very well. I already mentioned the keyword blocked force. This is extremely common nowadays, and understanding the blocked force, of course, is key to do some accurate transfer path predictions. Of course, you also have acoustic pressure, which is not the topic of this webinar, as we actually, as Kistler, we focus mainly on structural applications, structural measurement. When it comes to the planning of the TPA test, there are a couple of things that I suggest you to keep in mind. And to start with the goal, of course, of the analysis, keep in mind the type of load, contribution pattern, or performance prediction you want to achieve to select the right approach. Keep in mind that in transfer path analysis, the mathematical manipulations can lead to easily accumulate to errors that can be easily accumulated. So at the end of the day, you have to make sure that your measurement chain is very accurate so that you can achieve the best result possible. Otherwise, you might end up having rather poor accuracy on your predictions or your understanding. There are also requirements on the type of consistency and repeatability you might want to have. I mean, if you have, for example, multiple steering columns, you want to make sure that the data you are acquiring from each of these steering columns is actually very consistent and repeatable. So you don't want that every time you're measuring a different steering column, you have to wonder whether you have been acquiring data which is consistent. So consistency and repeatability are also very important keywords, as well as considering for each of the measurement technology, you have at hand the pros and the cons, and to make a choice which makes you confident that you're going to get a really high level of accuracy. There is also a second set of consideration I want to bring today to your attention. We have, through this whole introduction, often discussed about interface forces and the fact that acceleration sensors and force sensors might be used for TPA. And in fact, To estimate force at the interface, you might do a direct force measurement with a force sensor, but alternatively, we see more and more that forces might be indirectly estimated with accelerometers by placing accelerometers around the interface point, for example, and making use of the admittance metrics. There are some differences when you are performing direct force measurement or indirect force estimation, and I just want to point out our point of view on this. For example, of course, we start by saying that in the first case, the measure is force, and the second case is acceleration. This is pretty trivial. However, doing a direct force measurement has some pros, because first of all, as I just said, the measurement is force, and moments can also be estimated. The force is expected to be measured with high accuracy. And of course, when you organize a setup for force measurement, you don't expect to change it very often. Therefore, you will have a certain consistency and repeatability, for example, when changing the measured object and what you have to expect from it. Therefore, these are three good pros for the direct force measurement. On the other side, integrating a force sensor into testing objects will for sure require some engineering effort, so you have to plan for that. The packaging space in some cases might not be enough, so you have to make sure that you have enough space to integrate it. And the accuracy of the force measurement might be affected by the dynamics of the testing rig. Now, this is especially true at high frequencies. Earlier, I mentioned to you that there is no perfectly rigid block, and this is actually true. When you're measuring blocked force, you have always to make sure that you control and master the dynamic behavior of your block, so of your test rig, to make sure that the force measurement is accurate enough. On the other side, when it comes to acceleration, of course, acceleration sensors are easy to mount, position, and move. You're going to have to modify the testing object. They can fit very small spaces, and under certain conditions, they can be more accurate for measuring, for example, blocked force at high frequencies, because, like for example, with the in situ approach that I mentioned before, because here you have tools that allow you to minimize the influence of the dynamics of the test rig, for example. Of course, you need to be careful with that. And some of the cons are that, first of all, as I mentioned, the primary measurement is not force, and it is not moments. They are calculated indirectly. The accuracy of the estimation is, of course, sensitive to the amount of accelerometers that you're using, their position and orientation. So keep that in mind. And especially at low frequencies, you might have low accuracy. This is, of course, case dependent. It's not a general rule. It will require additional transfer function measurement, so you have to take that into account too. Estimating moments with accuracy might be challenging, and this is also case dependent. Of course, when it comes to a moment, you also have rotational degrees of freedom, so keep that into account. You need to make sure that you have consistency and repeatability in the data. If you consider the example I've given earlier, if you're going to exchange the testing object maybe in one month from now, you have to make sure that the accelerometers actually stay at their place and they are not used for another test, for example, because then if you do the setup once again, then there might be some little differences which will affect the accuracy of the final evaluation. And then finally, it is important in many cases to have a precise knowledge of sensor position and orientation on the geometry, because this will lead, then it will actually affect the accuracy of the prediction. So with this, I just wanted to give you our view on this topic, so that you have a good comparison between direct force measurement and direct force estimation before we jump into the next section, which is related to Kistler accelerometers for TPA. Now, when it comes to TPA, of course, acceleration is extremely used because it is a very important measurement in NVH in general. If we want to reach higher frequencies, acceleration is the thing you need to look at. They are easy to mount and position, and they are rather small, so they can cope well with with complex geometries and small spaces. How to select a sensor for TPA? Well, first of all, you generally would use a IEP, so sensors with integrated electronics and triaxial to maximize the amount of information that you can actually measure. And typically here you would have ranges in between 5G and 500 Gs. Here you have a small table which shows you how to orientate the choice for an accelerometer. What is very important is to have flexible mounting and orientation of the sensor, because you might often find yourself into small spaces, and fitting a sensor in a small space, this could be challenging, and you want to really place it as you wish. Having TEDs might also be a good feature. TPA generally is not done with 2 or 3 sensors. You will need more, and having the possibility to import all sensitivities from your sensors just with one click can really be something which can boost your efficiency. When it comes to hot areas, of course, hot applications like engines, you might want to look for a good thermal performance, and the frequency range, choose it aligned with the goals of your analysis. Of course, if you're analyzing the full vehicle, it is very seldom the case that you're going to go up to 10 kilohertz. But if you're going to analyze a sub-assembly, it may be that at least you want to analyze your data up to a few kilohertz, and the sensor must be ready to do that. A couple of months ago, we also have given a webinar on the selection of accelerometers for automotive applications. And if you're interested, please have a look at Kistler webpage. You will find on-demand webinars, and there you can register for that. Still another word about accelerometers and looking into the products Kistler can offer. Here we have 3 highlight products. The first one is 8763, which is available in a variety of ranges. It's a sensor which can cover up to 15 kilohertz, so it's quite broad range, I would say. And nowadays it has an improved electronics for which some of the sensor versions can reach up to 58 lower noise levels with respect to the past version. So it's a major improvement and makes this sensor even more suitable for FRF measurements, for example, and TPA, and wherever you have low vibrations like on electric motors, just to give you an example. The nice thing of this sensor for TPA analysis is that it has 3 holes, 3 threaded holes, and this allows you to orientate the sensor the way you want and the cable the way you want, as you see here in these pictures, which might make also the positioning and the recognition of the position a little bit easier during TPA processes. And for us, it's also a very, very good way to deliver you a very accurate sensor, as we can calibrate it on each axis independently. So very accurate calibration, and finally a wide variety of mounting solutions, which allow you basically to get an extremely flexible and versatile sensor for measurement. We do have also 8764, which is a sensor available in a variety of G ranges and still covers a wide frequency range. The special thing of this sensor is that it has a true hole, and therefore with the true hole, you can first of all orientate the cable in the direction you want, 360 degrees. So again, talking about the relevance and the importance of positioning of the sensor and the knowledge of the orientation, this is a key factor. And with a true hole, if you wish to maximize the connection stiffness, you can actually screw the sensor onto the surface, and this will ensure even more accurate measurements. One last point is that this sensor has an integral path, which will make sure you don't suffer from ground loops. So your measurements are going to be clean. And all this comes at a very low profile height. So this sensor is about 10 millimeters height profile. And by the way, the 8763 was around 11 millimeters, so also small sensor. Finally, we have a rather large sensors, which is the 8762, and it is larger because it allows you to go lower in G ranges. And I would use this sensor, for example, when you have to do FRFs on a body, where you don't suffer from the higher mass of the sensor itself. So here you can reach 5 or 10 Gs, and you still have the 3 holes, which allow you for easy positioning of the sensor. Additionally, of course, we offer impulse hammers, impedance heads for the shakers, cables and IEP force sensors to complement even more the product line. And to close, there is one last thing I want to talk to you about, and is the sensors for hot areas. And here is actually where we, as Kistler, can bring our PiezoStar crystal. Now, the PiezoStar is proprietary crystal from Kistler. We produce this crystal in our laboratories, and this crystal is very interesting for hot applications, because with respect to ceramic standard, industry standard ceramic sensing elements, typically the PiezoStar offers a wider temperature range, but while when you're changing the temperature, temperature measurement, the sensitivity of a ceramic element is changing. Therefore, while you're measuring, you don't know how accurate it is your measurement. The PiezoStar offers a thermal stability which is nearly perfect and is topping the market. This is not all. So having a wider, broader temperature range and a higher thermal stability is not all, because actually the nice thing of the ceramic element is that it can be miniaturized. Now, if you're moving to a quartz element, that cannot be miniaturized, although it offers better thermal performance. But the PiezoStar, it can go to dimensions which are comparable to a ceramic element. So if you're measuring with a ceramic and the PiezoStar, the same source, but the temperature starts to change, you will see that the PiezoStar still measures the same vibration level, while the ceramic sensor starts drifting a bit. The problem is that while you're measuring, you don't know that. And all this at the same shape factor. In fact, our 8766 has similar dimensions of the 8763 that you have seen before. It is available in a variety of G ranges. It's the same 3 holes on each side for flexible mounting, but it mounts PiezoStar, and it can have TEDs up to 165 degrees, which is quite remarkable. We also have a version which has a true hole, 8765, still has a PiezoStar in there, but it gives you the possibility to orientate the cable 360 degrees. It has an isolating pad, and you can actually maximize the connection stiffness. All these still with the PiezoStar in there. With this, I conclude the overview regarding the acceleration sensors, and I move then to a very interesting part for transfer path analysis, which is force measurement, our products for force measurement. And you might want to excuse me to give you a second crash course. This is going to really be a super short course in piezoelectric technology. So for those of you who are not familiar with piezoelectric technology, it is all based on the concept that piezoelectric materials under a mechanical load produce electrical charge. You see this in this picture. The element gets pressed, for example, you apply a force on it and you get charge. This charge gets gathered by a charge amplifier, which conditions this charge into a voltage signal. Now, if you take the piezoelectric element and you cut it in a particular way, in a certain direction, and you layer multiple crystal plates on top of each other, what you can get at the end is a force sensor, for example. So what you see here in this slide is exactly that. You have multiple sections of crystals or piezoelectric material, which each will measure in one specific direction. And at the end will give you a charge which is proportional to the force that you're applying in each of the directions. And that's how we have a piezoelectric force sensor. And if we take multiple piezoelectric force sensors, we can obtain a dynamometry, which is basically something which allows you not only to measure the forces in the 3 directions, but also possibly the moments, up to 6 components, 3 forces and 3 moments. And having said that, I want to give you an overview of how piezoelectric technology measures against a strain gauge, so a tensiometry strain gauge technology. So first of all, the piezoelectric measurement allows you to have rather high stiffness. And thanks to this high stiffness, you can actually have something which is highly suitable, especially for dynamic measurement. This high stiffness will also give you a rather broad frequency range of measurements, which we do like in NVH measurement actually. So we like even more nowadays with electric motors to go higher and higher in frequencies. Still, what the piezoelectric technology offers is a wide measuring range. So this is an example I really like, where we have the Rodin P530, which is a sensor I will show you later again for tire measurement. And actually here you have a range of 30 kilonewton, but if we place 50 grams on top of it, you see that on the measurement, you see exactly those 50 grams that have been added on a 30 kilonewton range sensor. So you see that the piezoelectric technology really allows you to get that. While of course the strain gauge might have some problems doing it. All the adjustment of the measuring range and signal conditioning can be done outside in the signal amplifier, in the charge amplifier. And another nice characteristics is that you can measure very small force changes with high static preloading. Now imagine you're putting an engine on top of a piezoelectric force sensor. You have a high static preloading, but you still want to measure vibrations. This is where piezoelectric can help you. You also have, of course, high repeatability, capability for overload because it's actually very stiff, and long calibration intervals. So you can calibrate with longer times with respect to strain gauge technology. Of course, strain gauge technology lends itself a little bit worse to high frequency measurement and dynamics because it works on a different principle. It works on, allow me to say, softness. So you have the deformation of an object, and you are actually measuring that deformation. So the object has to deform. The installation, it is easier though, so it's very easy to install strain gauges. There is no need for preloading, and of course you have somewhat easier handling of the cables because you don't have to preserve the charge. So this is a comparison between the two technologies. And if we go back to our original topic, which is TPA, I would say that in general, piezoelectric technology is more suitable for TPA applications. This is mainly because of the high stiffness of the piezoelectric element. And when you're choosing a sensor for TPA application, keep in mind the loading range. Try to understand as accurate as possible the type of force range that you need or moment range that you need, and try to exploit the available packaging spaces. As we will see, this is one of the main issues that are for force measurement. Now, when it comes then to Kistler products for piezoelectric force measurement, of course, Kistler has a huge portfolio of sensors, so it's extremely wide. It's really extremely wide. And what I try to do here for you today is to sketch a picture with probably the most useful sensors for transfer path analysis. Of course, go on the website, have a look if you find exactly what you need there, where you find all the products. What we have in terms of force sensors are single component force sensors in a variety of ranges. Some of them reached up to 200 degrees C. They deliver very high stiffness for broad frequency measurements and, of course, low noise thresholds. If they actually are not fitting your space, you might want to give it a try with the slim line. One component force sensors, which are available again in various measuring ranges, but what characterizes them is the small dimension. Have a look at this picture. This sensor here is an 8763 accelerometer. It's 10 millimeters side here, but the slimline force sensor is 8 millimeter diameter. So it fits a very, very small dimension. And we have them for vertical loading as well as shear loading. And then we have 3 component force sensors, again available in various measurement ranges, which again delivers high stiffness and for broad frequency range measurements. Now, of course, all these sensors must be embedded in some sort of case, which will also allow preloading. And to avoid that, to offer ready-to-measure sensors, we have force links, for example. And force links are basically force sensors, which are embedded into standardized cases, which are already preloaded and calibrated. and they can measure up to 3 directions. We also have sensors which can measure up to 6 components, as well as dynamometers which also can measure 3 or 6 components and are already ready to use for you to include them in your tests then. Some application examples of these sensors, for example, for blocked force analysis, you might have your specimen which is running at a certain speed or maybe multiple speeds, and then you have your mounting here with a dynamometer in between the mounting bracket, the mounting shoulder, and the block, and you're measuring blocked force. Or maybe the idea is not only to measure blocked force, but also to optimize the mounting. In these conditions, the dynamometer can be used, can be already ready to use, basically. Another example is this one on the right-hand side, where you might have an auxiliary drive or a motor, and this, again, you might want to measure the blocked force. Then what you're going to do is to connect the specimen to the block with our force links, for example. You see an example here on the top of the slide. And basically, thanks to the rest of the test bench for the motor, you're able to relate the blocked force to various operating condition of the motor itself. So it's it is a pretty simple setup where you can embed actually our force links and force measurement tools. However, we are aware of the fact that there are situations in which off-the-shelf sensors might not be enough. For example, the packaging space might be extremely complicated. I have many customers that are wondering how to embed the force sensor in an extremely complex packaging space. That the loading condition maybe could be kind of unique, so you have very very specific loading conditions related to the engine or to the motor. And then you might have a certain very specific environment. I mean, automotive, it's a pretty tough environment in certain cases. There might be special conditions also for the cables. Therefore, all these conditions make the applications unique, and you want to have unique solutions for these unique applications. And this is why what we do is to try to try to offer customized solutions to our customers so that they can really address 100% the needs in such critical situations. And here we can measure up to 3 forces and 3 moments. What we offer is fully tailored to the specifications and the geometry of the case. So like you see here, you see a picture of the initial component, which then gets transformed into a replacement, embedding 3 force sensors in there. And all these comes with 60 plus years of experience in sensor engineering. So Kistler has force product lines since more than 60 years. And really, when we develop this project, you clearly see that the long know-how in this area. And all this comes as a turnkey solution, starting with the design, production, calibration, which is a very important phase, because of course you can embed some force sensors into a case, but calibrating requires really specific know-how, which is able to translate the output of the sensor into something which is meaningfully related to the physics of the object you want to measure. And then, of course, commissioning and services are also part of our offer. And one thing that I also want to mention is that because we see that these applications are very interesting for our customers, we see the demand is more and more there, for example, for blocked force measurement or for interface measurement. Then we have a dedicated Kistler team that takes care of that. And this is the custom product lane. The custom product lane is made out of expert sensor in sensor engineering, which tries to develop the project as fast as we can so that we can support our customers with this type of issues. Here are some applications of the customized force sensors. You see here what we did was customizing a sensor with a flange so that it can be placed on a block to measure blocked force. Similar case you see here. Of course, when we design this, it's not just important the CAD of the component, for example, that can replace an original component, but also in general CAE, so having also finite element simulations which allow us to design the performance even before the sensor is put in production. And one important thing that we take really care of during for NVH application is the optimization of the natural frequencies so that they are as high as possible and they can really perform at best on the test rig. Finally, we offer a state-of-the-art calibration for these sensors. Here you can see our machinery for the 6 degrees of freedom calibration. This guarantees very high calibration accuracy, and of course, our processes ensure traceability. Now we jump into the last section, which is about wheel force measurement. What we see as mobility develops is, of course, that tire NVH is becoming more and more important for obvious reasons. However, what I have to tell you is that when I speak with customers or also with colleagues, it is actually a challenge to measure the force at the wheels. And this is why you often need wheel force measurement tools, even for TPA, because they can really give you this piece of information that is how much the axle, for example, get excited. Wheel force measurement tools allows you to get up to 3 forces and also moments at the wheel axis. So it's interesting information. Because of the way they're structured, they are rather accurate, repeatable, and also consistent in terms of measurements. So you can actually perform similar measurements again and again, and results are pretty consistent with each other. So you don't have to worry about that. The type of data analysis is could also go in the direction of being used for TPA applications because it's both in time and also angle domain. Of course, you don't want that the information is rotating with the wheel to avoid corrections, and this is, as you will see in a second, this is what we offer. And then the setup is rather easy. So setting up a wheel force or setting up a wheel measuring up is pretty easy to do. What we offer, as I just said, is wheel force transducers and wheel measuring ups, which we will see in a second actually. And starting with the last ones, which are the wheel force measuring ups. So basically, these are hubs which are mounted on the tire test rig. You see them here. Basically, here behind it, you see the rig, and here it's a roller, the drum of the bench that puts in motion the tire. Now, here is the principle of work, the working principle. Basically, you have the force which is traveling through the wheel and reaches the rotor, which is, of course, rotating. And then the force is transmitted to the stator, which contains the piezoelectric sensors or the sensors in general. And here, you're measuring the 3 forces and the 3 moments, basically, which get then extracted and processed. The design is pretty compact, so it's pretty small. And it can be mounted on the test stand, as I just mentioned. The structure is pretty stiff, so when it comes to measuring blocked force, for example, you don't have to worry really about this piece of a sensor. This is gonna, so the structure on which you have to put your attention is more on the rig and whether the rig might have resonances. So you have to focus on the stiffness of the rig itself. But this component has a very high resonance frequency. And finally, the measurement is taking on the non-rotating part. And now if you think about the type of analysis you want to do in TPA, this is an advantage, because at the end you will have an excitation which is staying in the the non-rotating coordinate system, so you don't have to correct it. For TPA application, as I just mentioned, measuring blocked forces and moments is very important with these type of tools. The consistency and repeatability you can have on the measurement side is pretty high, because of course, once this is mounted on the test rig, you can change tire, and the measurement tool will stay the same. And it covers generally the main structure borne range. So generally, you're pretty safe up to 1000 hertz. Of course, the resonance frequencies of these components here go far above 1000 hertz. And it's available finally in various dimensions depending on the vehicle tire and application that you have at hand. When it comes then to vehicle measurements. So, for example, on the road, we have wheel force transducers. Wheel force transducers are basically working like this. You have here the tire, which is exchanging forces through the rim and the flange. Then the forces are measured in high accuracy load cells, and then they get out and get analyzed. The type of design is modular. It is optimized for not only geometry, but also with respect to performance with finite elements. Depending on the size of the wheel, it can have from 4 to 6 strain gauge load cells. And it can measure 3 forces and 3 moments as well. These are basically calculated in the non-rotating coordinate system on the onboard unit, which is called key road. The output that you can get out of this measurement chain is both analog and digital. The operation is rather easy. Like for example, mounting the wheel force transducer is really extremely easy and can be done pretty quick. And finally, the calibration is done both at wheel force transducer level and at load cell level. So you can calibrate each of them. This delivers a very high accuracy, measurement accuracy. For TPA application, where can you use this type of wheels? Well, for example, for direct force measurement, when you're doing some on the road testing on the road, but also for validation purposes. The type of results they deliver are pretty consistent and repeatable, so you can rely on them even if they are done at a certain distance, at a certain time, one after the other. And they are also available in a variety of dimensions, depending on the vehicle and the application that you have. Here I report a sketch of the product portfolio for the Rodin family. We have products for measuring ups, for tire test stands, depending on the vehicle size. And of course, the output charge that comes out of these sensors can then be analyzed and conditioned with a charge amplifier or with a key road tire testing for the versions with strain gauge load cells. On the other side, we have wheel force transducers. You see here a wealth of products depending on the type of vehicle that you have, which can get analyzed with key road performance. This data acquisition system has basically a conversion at 16-bit up to 2 kilohertz and a cutoff at 500 hertz. Up to 24 channels can be acquired with this system. So basically, you can acquire quite a lot of data from the vehicle. Let's now jump into the wrap-up section. So what we have seen today is that TPA is a very important tool for NVH engineers, and I hope it is clear which are the key reasons for that. So all the benefits it can provide to the engineering departments, not only of OEMs but also of suppliers. Of course, accurate TPA results require a correct choice of the measurement tools. So you need to understand very well what you want to get and how to get there with the correct tools. Accuracy of your measurement tools is really key to get you to a successful TPA. And finally, I drove you through the Kistler portfolio for TPA measurement. And what we see basically are accelerometers. Of course, we also offer hammer and impedance heads. We have standard force sensors as well as customized force solutions when the applications are very demanding. We have seen wheel measuring ups and wheel force transducers for wheel force measurement. We offer also accessories and cables. We didn't go through it, but also charge amplifiers and signal conditionings are measuring tools that we do have in our portfolio. We can also apply strain gauges to components. This we didn't see today, but of course we can support you with that. We can measure, of course, torque. So we offer torque measuring flanges, for example, for electric motor testing when you want to compare. So when you want to calculate block force, controlling also what is happening on the motor. This is definitely possible. And another thing that might be useful to keep into account is the behavior of the engine. And therefore we offer powertrain analysis where together with the Keybox 2 recently launched, we can offer the in-cylinder pressure measurement. And having said that, I invite you to get in touch with us to discuss about the applications and how we can best support you to pick the right sensors. So get in touch with us, and we'll be very, very happy to support you. And with this, I give back the word to Eric and Adam, and I thank you very much for your time and your attention.
Yes, again, on behalf of Kistler, Roberto, and Adam, thanks for joining. Please look for the recording of this webinar, and it will also be posted on LinkedIn and other locations. So pass along to colleagues that maybe were unable to join, and we'll see you next time around. Thanks, everybody.
Thank you. Have a good day.